Thank you everyone for being here for the fifth and final press conference of the 246th meeting of the American Astronomical Society. It is Wednesday, June 11th at 10:15 a.m. here in Anchorage, Alaska. My name is Kerry Hensley. I'm the Deputy Press Officer for the AAS, and I'm going to be emceeing this session. I'm assisted today by Lexi Galt, our AAS Media Fellow, Susanna Kohler, the AAS Press Officer, who's assisting remotely, and our SPHEREx Media Intern, Maggie Verico, who will be assisting with the Q&A. All materials associated with yesterday's morning and afternoon press conferences have been added to the press kit. So please go to the press kit to find all the press releases, presenter slides, and the briefing videos from yesterday. Those materials for this morning's press conference will be available as soon as possible, and there will be several press releases associated with this morning's presentations. A brief overview of the ground rules in case this is your first ever AAS press conference. If it is, welcome. We're happy to have you here. We are recording this briefing and live streaming it to YouTube. It will also be archived on the Press Office YouTube channel, so you can check it out and send a link to anyone there. I'm going to give a brief introduction to the topic and our speakers. We'll hear from the panelists. We have 5 presentations today, and we'll hear from them in the order in which they're seated. They'll speak in order, one right after another, and then we'll go to Q&A at the end for all of the presenters. For those of you who are watching on Zoom, you can feel free to use the Q&A box to queue up your questions at any time. And I just want to remind you to please include your name, your affiliation, and who your question should be directed to. Finally, I'd ask that you silence your cell phone or anything else that might interrupt the briefing. Today, we're going to be hearing about recent and upcoming discoveries in the broader universe. So not only things that have already been discovered, but things that we can look forward to seeing soon. First, we'll hear from Harrison Souchereau of Yale University, speaking about inner tail gas asymmetries and fallback in a jellyfish galaxy. Next, Sean Linden from the University of Arizona will tell us about In the Belly of the Beast, massive clump formation in the hearts of major mergers. Then Isak Wold from NASA and the Catholic University of America will tell us about uncovering the drivers of reionization with JWST. Then Nathaniel Lujan from the University of Texas, San Antonio will tell us about the dark matter-dominated galaxy Segue 1 modeled with a black hole and no dark hole halo. And finally, Phillip Korngut from Caltech will tell us all about first light with the SPHEREx Observatory. And with that, I'm going to hand things over to our first presenter.
Hello, good morning. My name is Harrison. I'm a PhD candidate at Yale University, and today I'm going to talk to you about a galaxy that I've been studying called NGC 4858, which is a jellyfish galaxy in the Coma cluster. So to first understand jellyfish galaxies, we need to understand ram pressure stripping. And the easiest way to intuitively understand ram pressure stripping is to, if you imagine that you're driving in a car and you stick your hand or your head out of the window and you feel a wind on your head or your hand, you have now experienced ram pressure, and you're experiencing the same physics that galaxies in really dense regions, such as clusters, are also experiencing. So as a galaxy travels through the hot gas of a galaxy cluster, it experiences a wind. Now, galaxies are made of both stars and gas. The stars basically feel nothing at all, but the gas can often get ripped off. So the image I'm showing on the right, you can see this very dramatic gas tail kind of extending in the opposite direction to how the galaxy is moving. Now, since it only affects the gas, stars are unperturbed. Therefore, if we see stars out in the tail, this means that there has to be new stars being formed from the gas that has been stripped away from the galaxy and is now in the tail. And if we see stars out in the tail, which I'm kind of highlighting in this image as well, this is what we call a jellyfish galaxy. So the galaxy I'm showing today is NGC 4858, which is one such jellyfish galaxy. This is located in the Coma cluster, which is approximately 320 million light years away. It is traveling at approximately 56,000 miles per hour through this cluster, so a very high rate of speed. And you can see kind of extending north from this galaxy are these really brilliant blue star trails. So this is a very quintessential jellyfish galaxy. To get at, to understand what is going on with the gas in this galaxy, we observed it with the Atacama Large Millimeter Array, which is an array of radio telescopes in the Atacama Desert in Chile. And we observe effectively the cold gas in this galaxy. And what's remarkable about this data is, unlike a regular telescope where we only see the spatial information where this gas might be located on the sky, our ALMA data allows for a third axis, which is velocity. So I'm showing a sort of 3D rendering of the data on this galaxy, where you can see the two components, both the galaxy's gas disk, as well as those bunny ear-like tail features extending north from the galaxy. And so from this, we know not just where the gas is located on the sky, but how this cold gas is moving. And this allows us to understand the underlying physics of this galaxy on a much more fundamental level. This is only one such sample in this, one such galaxy in this sample, which covers 28 of the most extreme nearby examples of ram pressure stripping. And most of these are located in the Coma cluster, which was that galaxy cluster I showed in the previous image. So if we actually look at the distribution of cold gas in this galaxy, you might immediately notice that it looks a little bit different from the galaxy I showed a few slides ago. Mainly that the cold gas in this tail, those bunny ears, are located predominantly only on one side of the galaxy. So indicated by that black dashed line, which is oriented along the wind direction. The tail structures are located on the west side or the right side of the image. And what we think is going on here is that this is likely an effect of the wind first striking the galaxy in an edge-on way. So from the wind's perspective, it's seeing this galaxy more like that edge-on galaxy that I'm showing in the bottom left, as opposed to that more face-on galaxy next to it. And this means the wind is only seeing a small fraction of the total gas disk of the galaxy. And also, rotation of the galaxy becomes more important. So as you can imagine, if you're driving in a car, the faster the car is going, the stronger the wind will be. It's the same thing for this galaxy. And now there's a side of the galaxy rotating into the wind and a side of the galaxy rotating against the wind. And so the strength of ram pressure is going to be different across the total disk. Now, like I said, we don't just have spatial information, we also have the motion of the gas, which is a combination of rotational motion. This galaxy's disk is rotating, as well as non-circular rotational motion. So we're able to build a model for how we would expect the gas in the galaxy to be rotating. And if we subtract this away, we are left with these, what we call velocity residuals on the rights that I'm showing on the right. Now, because of how this galaxy is moving through the cluster, you would expect ram pressure to create these kind of blue features, which you kind of see dotted around this velocity residual map. However, you may notice at the base of these two bunny ear tail arms, a very red feature, which is actually moving in the opposite direction to what we would expect ram pressure to be doing to this galaxy. And through a lot of work, we've been able to determine that the only sensible explanation for this feature is that it's being caused by gas that has been pushed out of the galaxy's disk, but is now falling back into the disk, which suggests a much more complex evolutionary picture than we would immediately, I think, would be happening for a ram pressure strip galaxy. Now, following this, we were able to develop a model for how this inner tail evolution proceeds, where we think generally gas is first pushed out preferentially on the side of the disk rotating with the wind, where it's already rotating in the right direction, so it can be much more easily stripped. Then it still has orbital motion, and so its rotation then carries it to the other side, where it is now rotating against the wind, and this gas will eventually collect, and that is where we would expect fallback to occur. And so this actually happens. We can see this in simulations of galaxies where we take a galaxy and we place it in a wind tunnel. And if you strike the galaxy with an edge-on wind, which is what we think is happening for this galaxy, we see this kind of evolutionary picture. So the bottom row of the schematic that I'm showing, which shows the different evolutionary stages, shows this for the gas in a simulated galaxy as well. And this happens without any kind of spiral structure. Now, NGC 4858 has really strong spiral arms, and so you can manifest this kind of asymmetry without any spiral arms whatsoever. And therefore, the kind of two bunny ear-like structures that we're seeing in this galaxy is probably two entire spiral arm components that were stripped away altogether and are at different evolutionary stages along this kind of evolutionary track. So to leave you with a few take-home messages, the cold gas structure and motion in this galaxy is due to a combination of very highly inclined or mostly edge-on ram pressure, and as well as the rotation of the galaxy, which creates very complex evolutionary effects in the inner tail. We found cold gas fallback in this galaxy, and it has never been observed before in such a clear and unambiguous way. So this is a really interesting discovery for the Alma-Jelly team. And lastly, in the broader context, understanding these extreme events will give us insight into how the ram pressure works for galaxies where you can't as easily see these effects. So by studying the most extreme events, we can understand how this works for all types of galaxies in the universe. And I'll leave you with that. So thank you.
All right. First, thank you to the AAS for giving me the opportunity to talk to you all today. My name is Sean Linden. I'm a postdoctoral fellow at the University of Arizona and soon moving to Rochester Institute of Technology to take a faculty position there. So I want to talk to you today about massive clump formation in the hearts of local major mergers. And since the launch of JWST, there have been two main sort of discoveries that the telescope has been able to make when it comes to studying galaxy structure and the formation of clumps. And Maze et al. 2023 showed that when you take a census of all of the clumps that JWST has detected so far, and this is primarily done through lensing fields where the magnification is so high that you can actually now detect with the resolution of JWST individual star-forming clumps for the first time out to redshifts of as high as 10. And when you compile all of these detections so far, we find that clump brightness as a function of redshift shows a steady decrease to the present day, which means that clumps at higher redshifts were forming more stars, they were more massive and in general larger. And we also know through surveys such as SPHEREx and Cosmos, which are studying galaxy structure at redshifts 2 to 5, we know that the galaxies that have the most massive clumps in these imaging surveys actually often show signs of being tidally disturbed, which means that these galaxy interactions are driving these massive clumps that are forming at high redshift. And the problem is that as great as JWST is, we still rely on lensing and in many cases sort of are unable to study in detail individual clumps. And so what we would like to have is a laboratory in the nearby universe where we can actually study these kinds of extreme stellar systems with great detail. And we know from detailed hydrodynamic simulations of galaxy mergers that these massive clumps form in the densest and dustiest regions of galaxy mergers. So we need a sample of very dusty, extreme mergers where we can study them in their centers, where the gas densities and pressures are so high that they can produce these extreme clumps that we are now seeing at high redshift. And so that brings me to the Great Observatory's All-Sky LIRG survey. This is a campaign, this is a survey that was started in 2009, originally with the Great Observatories, Hubble, Spitzer, Chandra, and Galax. And we have imaged 200 of these galaxies across those telescopes. And on the left-hand side, I'm just showing you some of the examples from HST, two-color images of what some of these sort of extreme luminous infrared galaxies look like. So luminous infrared galaxies are galaxies with infrared luminosities greater than 10 to the 11, and ultraluminous being greater than 10 to the 12. So these are incredibly star-forming galaxies. They are incredibly rare in the local universe. Less than 1% of galaxies out to 400 megaparsecs would fall into these category. And so they're a great laboratory to study clump formation in major mergers. Now, the problem is that on the left-hand side, you see many of these, even with HST, we were not able to resolve the clumps in their center. And in many cases, the dust actually obscures HST's ability to detect clumps. And so on the right-hand side, I'm presenting new results from a Cycle 2 JWST program to do near-cam imaging and near-spec and MRS spectroscopy of the central regions of a handful of these ultraluminous infrared galaxies. And what you notice immediately is that we are able to detect hundreds or actually thousands of clumps in these systems down to the very center, where JWST can now look through the dust. And to reinforce this point, if we take one of these galaxies and we flip between HST and JWST, you see that in HST, that the sort of eastern nucleus is completely obscured by dust, and we miss all of the star formation that's happening in that region. And if you focus on the overlap between the two nuclei, you see these incredibly red clumps that pop out in the center. And these clumps are the sort of youngest and most dusty clumps that we're looking for, because we think that these are the sites of the most extreme star formation that we can potentially compare to the high redshift universe. And we know that from initial studies, at least 20% of these sources are undetected at optical wavelength. So they truly are being revealed now for the first time with JWST. And so as a quick summary of what we have found here, on the left-hand side, I'm showing the distribution of clump luminosity detected in our ULIRG survey. And there's two lines here. In blue is the all of the clumps detected with NearCam. And in red are the sort of dustiest extreme clumps, those ones in the overlap region that I was showing you in that movie. And you can see this flattening of the luminosity function from about -2 to about -1.5. Now, if we look again at that detailed hydrodynamic simulation that I showed originally, this is the exact prediction that these simulations make. Is that on the x-axis here, I'm now plotting the density of the ISM, or the pressure. And so again, when you go into these extreme regions of galaxy mergers where there's a lot of dust, and we can reveal the clumps that are forming there, we find in red on the left-hand side a slope that is very consistent with the simulations of about -1.5. This is the first time that we've actually been able to verify observationally that the properties of these extreme clumps actually match what we're getting in detailed simulations, and also match what we're now seeing at high redshift. And so we're able to sort of, for the first time, bring the local universe and the high redshift universe together to study massive clump formation. So I'm just going to leave my summary up. Thank you very much. Yeah.
Okay, hi, I'm Isak Wold, and I'm going to tell you today about a population of tiny but mighty galaxies that help reshape the universe. So this image is showing the massive galaxy cluster, Abell 2744, also called Pandora's cluster. And this is a cluster that we use as a cosmic magnifying glass to find very distant galaxies that glow brightly in oxygen due to young stars. So here is a cartoon picture of the history of the universe, with the Big Bang on the far left and the present-day universe on the far right. And within the first billion years, the very first stars and galaxies formed and emitted energetic light that stripped electrons from hydrogen atoms throughout the intergalactic medium. This is the gas between galaxies. And as a result, about 90% of the universe's hydrogen became permanently ionized. So there's still significant debate over what powered this epoch of reionization. Was it big or small galaxies, or what role, if any, did massive black holes play? So to investigate, we conducted a survey specifically targeting the smallest, youngest, most energetic galaxies at a redshift of 7 to test whether tiny galaxies could reionize the universe on their own. So this is a redshift of 7. This is towards the end of the epoch of reionization. So I claim that to be prime suspects for these drivers of reionization, they must meet 3 requirements. So number 1 is that they need to produce a lot of ionizing light. This is high energy ultraviolet light that's able to ionize hydrogen. Second, this light must find a way to escape from the host galaxies. And finally, if the more of these objects we have, the better to help explain this major phase transition that's occurring throughout the universe. So galaxies that glow brightly and doubly ionized oxygen, I'm going to be referring to these objects as oxygen-3 emitters, we know that they're very young starbursts that produce lots of high energy ultraviolet light. Recent studies from James Webb shows that these oxygen-3 emitters at early cosmic times punch above their weight, producing even more ionizing light than expected. Locally, they're known to have some of the highest escape fractions, and while they're rare in the local nearby universe, they are relatively common at early times. So I'm claiming that these oxygen-3 emitters meet these 3 criteria to be the prime suspects for playing a major role in reionization. So we looked for these objects within this cluster field, this Pandora cluster field, which was imaged by Webb as part of the publicly available Uncover program. So within this field, we found a large number of oxygen-3 emitters, 83 objects, and we were able to spectroscopically confirm 20 of them with Webb's NIRSpec. So I've highlighted here the 20 objects that are now spectroscopically confirmed. So now let's zoom in to the central region of the cluster, shown by this white rectangle, and look at 3 example galaxies, which I've highlighted in green. So if we zoom in one additional time, you can see that these oxygen-3 emitters are very small, they're compact, and in this color composite, they appear green. So this green color is coming from the medium band filter, which is centered at 4.1 microns, that captures the strong oxygen-3 emission at a redshift of 7. So thanks to this medium band selection, along with gravitational lensing, we're able to detect galaxies with stellar masses as low as a few million solar masses. So I'd like to highlight the object that is in the center here. So this object is magnified by a factor of 11 by the galaxy cluster, and we find that it has a stellar mass of 2 million suns. So this is comparable to the largest star clusters within our own Milky Way. And so then for these objects, we have spectra for all of them, and we find that, as expected, they lie at a redshift of 7. And then this green color that we're seeing, as shown by the medium band, is caused by these bright oxygen lines, as we would expect. So this follow-up with NIRSpec, we not only see these 3 characteristic strong lines, but we see a host of other lines. And with these lines, we can determine their physical properties. And we find that they are young, nearly dust-free metal-poor starbursts, conditions that facilitate the escape and production of ionizing light. So given these properties and their known numbers within our survey, we can better estimate their contribution to reionization. So previous surveys of oxygen-3 emitters could account for about 40% of the ionizing light required for reionization. But with our sensitive medium band selection and the gravitational lensing provided by this foreground cluster, our survey is 10 times more sensitive, giving us a larger sample that can supply all of the light needed for reionization. So here, we are assuming that 25% of their ionizing light is able to escape, which matches what we see in similar galaxies nearby. So in summary, we've employed this sensitive medium band search along with gravitational lensing, allowing us to go 10 times more sensitive than the previous survey. we find that these objects are young, nearly dust-free, metal-poor starburst conditions that facilitate the production and escape of ionizing light. And if 25% of this light is able to escape, as nearby analogs suggest, these tiny but numerous galaxies could produce all the light needed for reionization. Thank you.
Good afternoon, everybody. My name is Nathaniel Lujan. I come from the University of Texas at San Antonio, and today I'm going to tell you all about this strange dwarf galaxy called Segue 1. Now, before we get into it, what is Segue 1? Well, it's been described as a fossil galaxy. I'll get into why, but what we'll point out specifically is that it has a mass to light ratio of over 1,000, which simply means that there's far more dark matter than there are stars in this galaxy. And we're talking about a lot because in the core of this galaxy, we can only really see like 100 stars. So we're like, where's all this mass coming from, right? This galaxy also comes very close to the Milky Way, only about 23 kiloparsecs away, and has a wide varying metallicity of the stars, which I'll come back to. So if Segue 1 is completely dark matter dominated, how would we possibly simulate or find out what's going on in there? Well, we're actually going to go back in time a little bit, and we're going to use what's called orbit superposition modeling. And so what orbit superposition modeling is, it sounds like something out of a quantum textbook, but it's not. All we do is we get a library of 20,000 stars. We define a gravitational potential, and then we allow those stars to go through that gravitational potential. And so if you watch my video here, I have 5 stars circling around a gravitational potential that actually best describes Segue 1, and I'll get into the parameters that we use to define this. Okay, so we have to test all the possibilities, right? So I have to define the gravitational potential. I have my stellar orbit library of 20,000 stars. I'm going to define my potential using 4 parameters. The mass to light ratio of our galaxy, which is ultra dim, possibly a supermassive black hole mass, right? The circular velocity of our stars that we can see, and the radius of a dark matter halo. Okay, so this is 100,000 runs that I ran. The teal points are going to be a 4-parameter fit of the galaxy. The blue will be no black hole, and the red is a no dark matter halo. And as we can see, it's a terrible fit, not doing all 4 parameters. So we have to do a 4-parameter fit. And all I'll point out on this slide specifically, because we'll do a zoom in on the supermassive black hole, but is that the best fit is actually tending to the dark matter halo's smallest limit that the model will allow. And that's actually where I found our best fit. And so this is a close-up view of me searching for the black hole mass. This is done manually, so I submit like 5,000 runs at a time, and then analyze it, see where we're at, and then try again. And so you'll see me filling out the parameter space. Here we go, and boom, there it is. All right, so what is this telling us? Well, Segue 1, this dark matter dominated galaxy, could be hosting a supermassive black hole of 500,000 solar masses. Crazy. And regardless of dark matter profile, NFW or core, we find that the dark matter, the supermassive black hole mass is unchanged. Which is amazing because Segue 1 is a galaxy we can hardly see, but I'm suggesting that it hosts a 500,000 solar mass supermassive black hole in its center. So how so? Well, this could be because Segue 1 is actually kind of lying to us. It could actually not be, or it is currently a dwarf galaxy, but it could have started as a much larger galaxy. And due to its close interactions with the Milky Way has siphoned off gas and stunted star formation in the galaxy, which is prominent in the wide range of metallicities that we see in the stars. suggesting intermediate star formation as the galaxy orbits close to the Milky Way. So if that's the case, then well, it's no surprise that there's a supermassive black hole there. It is a concern that we were just simply saying it's dark matter dominated, but if we know the whole story, it kind of makes sense. If that's not the case, however, and Segue 1's not, our own homegrown little red dot, then it could be that the rarity of supermassive black holes is actually misunderstood in these regions. So future works, I would like to apply this model more expansively to other dwarf galaxies in the region, such as Draco dwarf galaxy, of course. And I would like to upgrade our model because the current model, as I said, it was kind of old, but it is being implemented now because we're able to use supercomputers and graphics cards. So I would like to upgrade the model language to implement Python and Julia and do some AI to find that potential so that way I don't have to manually do it, as that takes a lot of computing hours. With that being said, this concludes my talk. I would like to thank my advisor, Richard Anatua, and my co-author, Carl Gebhardt. And I would like to thank the AAS for giving me this opportunity to talk to you today. Thank you.
All right. Well, my name is Phil Korngut, and I'm the instrument scientist for the SPHEREx mission, and I'm super excited to be here today in Alaska to show you some exciting new data that's coming out of our observatory. So, SPHEREx is a brand new object in low Earth orbit. You can see here just a few months ago, March of this year, our beautiful separation into our new home in a sun-synchronous low Earth polar orbit. That was March 11th. We then took the next month and change to commission our new observatory. So we call that IOC. You can see us here in the control center at JPL. We carefully and systematically powered on the observatory, making sure everything was working, and it came on beautifully. And along the way, took some of our first images, which I'm very excited to share with you here today. Just to take a step back, SPHEREx is NASA's newest space telescope. It is a mid-X class mission, and at its core, it's an enormously wide field of view, near-infrared survey telescope. Now, we specifically tailored this survey to get at our top 3 science goals. Very cursorially, I'll just mention we are going to survey the plane of our own galaxy, looking for biogenic ices such as water through absorption line spectroscopy. We're going to get at the history and evolution of galaxy formation through studies of the extragalactic background light, and study the very earliest epochs of our universe through large-scale structure studies. And all of these 3 things are united in that they require an enormous spectroscopic survey in the near-infrared. We do this using a technique called linear variable filter spectroscopy, which is somewhat different than what you're used to seeing. There's no slit or grating or prism. We just have these 3 filters which sit over our field of view, and they're linear variable filters. So each pixel has its own wavelength response, its own spectral response. And you can see in this movie how we dither our field of view across the sky, putting each position of the sky onto a different position on our field of view. And by doing this over the course of 6 months, we're able to survey the entire sky. I'll just restart that. By dithering this. And our baseline mission is to do this 4 times over the course of 2 years, producing an enormous spectroscopic data set. So what do these data look like? Well, here's what we saw on our very first command to take an image. This is a very different data product than what the community is probably used to looking at, so let me walk you through it. First off, this is an enormous field of view. So that's 11 degrees on a side by 3.5 degrees, and you're seeing it in 3 positions here. SPHEREx also uses what we call a dichroic beam splitter, which is an optic that behaves like a mirror at certain wavelengths and a window at others. So we're simultaneously imaging that same chunk of sky in 2 broad infrared channels. The color scale in this image we've coded here not to contain intensity information, but the actual wavelength that we're measuring that position of the sky on, and that's color coded in that that color bar there. We're operating between 3/4 of a micron and 5 microns contiguously across this field of view. If we zoom in on a few things here, you can see those bright stars, and then of course in the band 1, you can see a big band coming across. That's spectral line emission from our upper atmosphere in the Earth. And it's a great illustration of how a linear variable filter works. You're illuminating the entire focal plane, but you just see this stripe because it's a monochromatic illumination. If we zoom in there, you can start to get a sense of just the scale of these images. I'll zoom in again. You can see there a bright foreground galaxy, and we zoom all the way in. You can see every little dot there are faint distant galaxies. And this is a single exposure. We take about 600 of these a day, and we do that nonstop for 2 years, building up our spectral data cube. This is also fantastically useful for mapping diffuse structures. Here's an image kind of on the outer coastline of the larger Magellanic Cloud. This is at 3.3 microns, PAH emission. But to understand how SPHEREx makes these maps and the power, it's best to really start to look not in images, but in movies. So here you can see a linear variable filter. We're fixed now in celestial coordinates, and each frame of the movie just moves what position of the focal plane is measuring what position of the sky. And you can see as we zoom in on this region of action here, the PAH, and also simultaneously on the other side of the beam splitter, we're seeing S3 in band 1, and you can just see all of these structures and the molecular and atomic emission just lighting up, and there's a wealth of information in there. Now, as we progress with our operation of the observatory, we have now gotten to the point where we have pieced together full data cubes, and I'm excited to show you that here today for the first time. Naturally, in our orbit, we have 2 regions around the ecliptic poles that are built up we cross them much more frequently. So what you're looking at here in the background is a broadband image. So this is kind of a traditional astronomy image where we have co-added down all these wavelengths. We just show you this to give you context. This is only about 5 square degrees at the ecliptic pole. This is made with something like 2% of what will eventually be a single survey. And every single dot in this image is, the faint dots are galaxies, the foreground, bright stars, and everything else that's in between. And of course, the real power of SPHEREx is not in this image. It is that in every pixel of this image, we have a spectrum. So there happens to be a green X on one of those pixels. So let's zoom in on what's going on there. And now we're showing you a swim through our data cube. There's a planetary nebula right in the center of that. And then we can see as we go across, you can follow the wavelength and the tidal there. The geometry is changing here. You see diffuse structures lighting up. The core has its extended halo, and we're looking at mostly emission lines from hydrogen series, the Fund series, bracket, alpha and beta, along with H2, S3, there's all sorts of lines which light up at different wavelengths, and you can just see. I'm not showing this to really highlight, the planetary nebula science. I'm just showing that every single pixel in this image will have a spectrum across the near infrared, and of course, not just this image. Everywhere on the sky will have a near infrared spectrum. So no matter what object you're interested in, as long as it's above our detection threshold, we will deliver to you, the community, a spectrum across the near infrared. This is where we're at right now with the SPHEREx survey. Just the first month, we activated full survey operations on May the 1st of this year. And this is a different kind of coverage map than you're used to looking at, because the color scale here tells you how many wavelengths we've observed it at. When we get to yellow here in 102 wavelengths, we have a complete spectrum, and we are marching along, filling up the sky with spectroscopy. These data are going to be shoveled out to you, the community, starting in just a few weeks' time. In early July, the first release of calibrated spectral images are going out to the community. They are served up at NASA IPAC hosts the URSA server where everyone can go and get these spectral images. The initial release will contain about a week and a half, and then we just roll out the data on a conveyor belt to you, the community, to just have at it. There is just such a wealth of information in this spectroscopic data set. We're obviously excited to get at our goals for science, but really the discovery space is wide open. So I'm looking to you, the community members, to go fishing for some amazing spectroscopic results. And thank you very much.
All right, with that, it's time to get started with our Q&A. For those of you here in the room, please raise your hands high so that Maggie can see you and bring the microphone to you. And for those of you in the room and online, please remember to state your name, your affiliation, and who your question is for. So first, let's open things up here in the room. All right, Kala first.
Thank you. Kala Perkins from Ubiquity. Phillip, what redshift is the deep field from SPHEREx at?
Oh, well, it's because we're just taking a broad survey. It contains information from the entire integral of redshift history. So there will be photons in there going all the way back, and we're going to study through intensity mapping as a technique where we're actually going to disentangle that light field. But a shorter answer to your question is the most of, based on our wavelength range, the peak in our galaxy density, if you're interested in studying objects, is probably going to be from 1/2 to 1 around there. But it contains signal that's integrated all the way back to rest frame UV at the epoch of reionization, which we're ultimately hoping to constrain through these intensity mapping studies.
Thank you.
Hi, I'm Richard Anantua of the University of Texas at San Antonio and Rice. Great talks, everyone. I have a question for Harrison. With the different components of these jellyfish galaxy moving at different rates, can you get information about the underlying dark component structure? You can think of the bullet cluster as being a classic example of how we can isolate the structures of dark and gaseous and dusty components.
So you're talking about dark matter?
Yeah, the dark matter components.
With this galaxy, generally, the dark matter will probably be baked into any kind of rotation curve of, say, the remaining stellar disk of the galaxy. Ram pressure doesn't affect dark matter itself. So perhaps other effects in the cluster, like, say, tidal stripping, might remove dark matter from galaxies as they travel. But with ram pressure, it's not immediately clear if we're able to say anything in particular about how the dark matter is, say, evolving in these galaxies.
Ethan?
Thank you. This is one of my favorite press conferences. You guys were all awesome, and I could bother all of you, but I won't do that to Kerry yet, who hasn't been asked a question. Nathaniel, I was really impressed by your talk, and when you talk about Segue 1, I'm familiar with previous studies that didn't really look at the they didn't take the idea that there would be a supermassive black hole in the center very seriously. It was really talked about as this is a dark matter dominated galaxy, as we infer from the velocity dispersion of the stars. And I thought, well, you're talking about a black hole that's comparable in mass to the assumed entire mass of the dark matter halo. And if that were the case, I would think as an independent check of that scenario, you would look for high velocity stars taking a plunge close to the central location of that galaxy. Now, I know there are only a few hundred or thousand stars in this galaxy. When you look at those stars, do you see any potential candidates for, oh, it's not moving at 30 kilometers a second, it's moving at a significantly larger number? Do you see any high velocity stars near the galactic center?
Yes. So
yes, tell me.
So when we do alter like our models, we do see that the velocity of those central stars, 100 stars, are just going up very high. No, I not off the top of my head, I can't. I'm sorry. I think it was on my it's on the slides. But No, we do see some circular velocity going up from those stars. I do think that we'll need to adjust the model to allow for a smaller scale radius for the for the dark matter halo, and I think at that point I could give you a more grounded answer, just because this is more of a tool to determine whether we should even be looking well, how much dark matter we should be looking for, I guess. Yeah.
Further questions in the room? Maggie?
Hi, I had a question for Isak. So you said that you are able to explain the reionization of the universe entirely with these dwarf galaxies. How does that impact our understanding of the epoch of reionization?
So I think it indicates that we can easily explain the sources of reionization with these low mass dwarf galaxies. And so it's from this work, I wouldn't, you don't necessarily need to look for more exotic features that like, a significant black hole type source. So I think we are able to explain this with numerous low mass galaxies. And so I think that when we're looking at this great awakening of the universe where the first stars and galaxies are forming, our interpretation is that we favor these numerous low mass galaxies playing the dominant role.
Hi, I'm Gary Melnick from Harvard Smithsonian Center for Astrophysics. I also had a question for you, Isak.
Sure.
Oxygen 3 also has far infrared lines. The oxygen 3 line at 88.35 microns, for example, is quite strong in Milky Way nebulae.
Mm-hmm.
Have you thought about looking at redshifted O3, far infrared O3 with ALMA? The advantage there being that whatever residual dust there is in this galaxy will be totally transparent to that line. You don't have to worry about any attenuation.
Mm-hmm. That's a good idea. I have not personally thought too much about that yet. Been busy just having fun with this the data that we have currently, but I think that's a good idea. I think that from the spectroscopic characteristics that we're seeing is that there is not very much dust. So I think that much of the oxygen 3 that we're seeing optically is probably a good indication of how much there is, but it would be interesting to follow it up with more.
This would be a good test of that assumption.
Yeah.
Because the 88 micron is definitely unaffected by the dust.
Yeah, and the reason why I'm saying that it's dust-free is we're looking at Balmer decrements, so H alpha to H beta seems to be an indicator with our sample that there's relatively little dust, but I agree, more data would give us a clearer picture.
Ethan?
All right, there's a risk I will go until she stops me. So I want to start. Sean, I don't think you've gotten one yet, so I'm going to give you the one I have for you. When you talk about these major mergers and using these nearby galaxies as analogs of the major mergers in the early universe, one of the things I learned from JWST is when you see in the infrared a really bright set of diffraction spikes in the galactic center, it tells you one of two things. Either you have a big, bright, ongoing burst of star formation right now, or you have supermassive black hole activity. And I noticed when you showed some of these galaxies that were seen previously, not with JWST, and then you look with JWST, boom, big, bright diffraction spikes in the center. What did I want to ask? Oh, yeah. Have you been able to determine what sort of central galactic activity is present in these nearby galaxies? And do they have implications for what we see at the high redshift analogs of them?
Yeah, that's a great question. Thanks. So indeed, in those images in the near infrared, when you see diffraction spikes at the center, in all of those cases for these ultraluminous infrared galaxies, those are active galactic nuclei. So they're actively accreting massive, supermassive black holes. And one of the things that I did not talk about is that We have spectroscopy in both the near and mid infrared from JWST that allows us to study the properties of the black holes themselves, of the outflows that these AGN might be generating, and the impact that those would potentially have on the clumps that are forming in the very near vicinity. We already have some examples from earlier work in the GOAL survey that the black hole, the AGN destroys a lot of the small grain dust near in these clumps. And so potentially the dust in the gas is fundamentally altered when forming these very massive clumps near AGN. So yes, we're actively looking at that. And it could have implications for these things like little red dots. We still don't really know what they are. You know, many of them look like they're AGN. Some of them look like they could be, you know, sort of nuclear star clusters. And so there's this congress of AGN for activity and star formation in the early universe that we have a very hard time getting a really detailed handle on because just how far away these galaxies are. So in that sense, there also could be analogs. Yeah.
Do we want to, oh,
I
go
can do
ahead.
another
We've
if,
got a question online we'll go to.
okay. All right. I guess my next one will be for Harrison, because even though you've been asked a question, it wasn't from me. I was curious about the bunny ears you were talking about. And there was a thing you said that confused me. So maybe you can clarify. Why would the bunny ears be stripped spiral arms? I would think that spiral arms are rich in both dust and gas and stars. And I would think it would be very difficult, even with ram pressure, to strip stars out of the galaxy, that the cross section is just all wrong for their conservation of momentum. So why is this stripped spiral arms rather than stripped gas that was compressed by the ram pressure and then formed new stars as a result?
Oh, yes. Your explanation is precisely correct. So I believe it's the gas in the spiral arms that were stripped away from the disk. And then as they're kind of orbiting or rotating across the inner tail, then they're forming new stars along this kind of evolutionary pathway. So yes, none of the stars in the disk are getting stripped. It's just the gas within those spiral arms. Furthermore, the reason why we think that these entire components are being stripped kind of all at once is that we think that there's a preference for stripping on one side of the galaxy. And so this kind of preferential stripping would lead to entire clumps of spiral arm gaseous components being stripped all at once. And this is probably happening simply because the ram pressure this galaxy is experiencing is very, very extreme. It's the most extreme, at least line of sight velocity that we have for galaxies in this extreme ram pressure stripping sample. So it's probably the fact that you get full components being removed like this is probably helped along by this very extreme ram pressure.
Give someone else a chance.
All right, we'll go to a question online, and then I know there was another one here in the back.
So we have a question online from Jean Malone that is for Nathaniel. And it says, I may have missed this, but is there any model that you tried where the dark matter halo is required? In other words, is its presence in this galaxy neither necessary nor sufficient?
That's a great question. So the 4-parameter fit that I did includes the dark matter halo. So we got the best fit of the galaxy, so description of the galaxy using a dark matter halo, but it just had a significant less impact on the gravitational potential because 500,000 solar masses are in the supermassive black hole. Yeah. Thank you.
I'm
Lexi
going
has
to
a question.
ask you a semi-related question. Does this galaxy have any gas mass in it, and did you consider neutral gas or anything when you were modeling it?
Yeah, so we actually modeled it isotropically. And so how we did that is we removed any gas or stars that were being stripped as they didn't really add to. Yeah.
Hi, I'm Charisma, a grad student at MIT. I'm so excited to hear about the SPHEREx updates. I have a question for Phillip. with what we know now, how will the near-infrared spectral resolution via NIRCam, do we know anything about the identification or cartographic analysis for like water compounds, that it was a search for life or a search for those compounds? So if there's any direction with the updates for the search for life?
Yeah, absolutely. So you mentioned NearSpec. So we're fantastically complementary to something like NearSpec. NearSpec has, they have a giant light bucket and they have fantastic spectral resolution, but they have a tiny slit on the sky, right? So they can look at individual objects and give you fantastic absorption spectra, including water ice, which is really what SPHEREx is about. So for SPHEREx, we have also in that wavelength coverage, great optimized for sensitivity on water ice absorption. So we're going to survey, though, millions of lines of sight all along the galactic plane that have been identified as good candidates for having water ice along the line of sight. So we'll deliver a huge catalog of potential candidates. And for instance, NearSpec would be a great thing to go follow up on the interesting objects. So it's kind of a dynamic range complement to those other capabilities that are coming online. And yeah, we're gonna make a real census of and other biogenic ices in the galactic plane.
All right, I've got two more because there's two of you I haven't given a question to yet. So Isak, I'll go with you first. This is, I think, a pretty big question. I'm familiar with earlier studies, including from Uncover, that have looked at the big bright galaxies that we've seen with JWST, because that's been, the stuff a lot of people have been talking about. And they said at most, from what they've been finding, these big bright galaxies can only contribute up to a maximum of about 20% of the photons we need for reionization, which means that these smaller, lower mass ones have to be, in some sense, the dominant fraction. So I'm curious, can these O3 emitter galaxies, these O3 emitter starburst galaxies, make up for a dominant fraction of the rest? Have you been able to quantify of the photons you need? How much do these galaxies contribute based on what you're seeing and what you expect the unlensed population of these galaxies to be?
Yeah, so I mean, that's what we're trying to get at is, we are taking the amount of oxygen-3 light that we see within our survey volume, and we're using that combined with the spectroscopic properties that we're getting from NIRSpec to estimate how much ionizing light is produced by our sample. And the thing that we cannot measure directly is the escape fraction. And so for that, we're relying on local galaxies that have similar spectroscopic properties to our own. And so when we try and match up our sample with these nearby analogs, we would expect, based on that, for them to have an average escape fraction of around 25%. And if that's the case, then we can explain with our sample all of the ionizing light that's needed for reionization.
So 100%.
Yes, and we are, when we calculate this, we are integrating our luminosity function, or we are integrating over all of the objects that are emitting in oxygen-3. So it's taking our sample, which my paper earlier this year is presenting the counts within our survey volume, giving us how much light, oxygen-3 light, is within our survey. And so this is also taking into account the bright end of that luminosity function, which is better constrained by a different survey that is going over a larger volume. So we're incorporating our faint end results along with bright end results and integrating over all of the oxygen-3 light that's within our survey volume to estimate this. All of the ionizing light can be produced by these oxygen-3 emitters.
Well, that's pretty cool. I'll have to check out the paper. Thank you. Can I give one more to Phil? All right. Thank you, Philip. I was really impressed by this. I hadn't seen like an animation of the SPHEREx filters in action before, and it's really cool to see how it just kind of moves over the field and gives you a basic like panning movie across wavelengths through it. I'm curious about the spatial resolution and magnitude sensitivity of SPHEREx? Because I know it's not a very large telescope, but having an all-sky near-infrared spectral survey that can get the whole sky is huge. I'm curious how this compares to any previous. Has there ever been a near-infrared spectral survey before? How does it compare to previous ones? And can you talk about how this will complement Rubin, which is going to give you this all-sky photometric deep survey?
Yeah, great. A great question. So with regards to the spatial resolution, so we've actually optimized our survey to put as much light from each object onto a single pixel for sensitivity, right? We're not imaging, we're not Nyquist sampling our beam as most do. So our pixels are 6.15 arc seconds, which is reasonably coarse compared to other surveys. But of course, the power comes from the absolute, the width of it. I'm not big on superlatives, but I do think this is the first spectroscopic all-sky survey. I think across wavelength ranges, of course, I don't like to get into, the qualifiers of, is 10 bands of spectrum. I would say 100 channels is very clearly into the spectroscopic range. But in terms of depth also, in the all sky, we are going to be 5 sigma AB magnitudes around 19.5, and about 2 to 3 magnitudes deeper in the deep fields. But our sensitivity varies across the sky based on the survey pattern. And there's a diagonal light foreground, which is our dominant noise source of photon noise. I think there's fantastic synergies to things like Rubin and those earlier, the optical ground-based surveys. One thing we are not great at, which they are great at, is time resolved things, because our survey pattern is a little bit, we only image a certain chunk of sky on these kind of interesting cadences, with the exception of the ecliptic poles, which we cross every orbit. But yeah, I mean, if you look at the Galaxy SEDs, many of them will peak around rest frame of 1.6 microns, which is why we chose our wavelength range. So while, the big optical telescopes can go much deeper in terms of magnitude sensitivity, the galaxies are a lot brighter in our wavelength. So it's comparable objects. And absolutely, I think there's going to be lots of synergy with those sorts of things. Photometric redshifts from the ground, and we'll have our low resolution spectroscopic, and then, comparing in smaller subsamples with other ground-based, high resolution spectrometers, I think is going to piece together a really nice understanding of the cosmic volume and the systematics associated with photometric redshifts, our kind of low spectroscopic redshifts, and just scaling that up to the largest scales.
With that, we're going to bring our press conference to a close because we're a couple of minutes over. Thank you all so much for being here, for your attention, and for your questions. Thanks also to the public information officers who helped to prepare press releases associated with this session. And I do, of course, want to share the date and time of our next press conference, if you'll bear with me here for a second. With my technical difficulties, I'm so excited to announce that this is already public knowledge. We will be in Phoenix, Arizona, early January next year. I hope you'll be there for JWST 247 for more press conferences. That's it for this week. And finally, let's just thank our speakers one last time with a round of applause.